In this video, I introduce Insight white box hallucination detection using internal states of large language models. Given a context X, a large language model F predicts the next token YT conditioned on the context X and the previous output tokens Y. P denotes the maximum softmax probability of a token YT. The sequence uncertainty or inconsistency is defined as a negative joint probability of a sequence of tokens, as shown here. Since the shorter sequences have a lower complexity, the joint probability is normalized by the length t to remove the factor of output sequence length. The uncertainty or inconsistency of the entire sequence is computed by using multi-generated responses for the same property, as shown here. Where key responses Y are generated by a large language model using the same input context X. When a large language model has uncertain or inconsistent responses, it generates a hallucination that results in output distribution with a higher entropy. White box insight uses the internal state of a large language model to detect the hallucination by measuring the semantic divergence in the sentence embedding space, as shown here. This is the input tokens. Insight uses this internal state to generate multiple output sequences. And then SVD are used to find the eigenvectors from covariance matrix. And then from this Eigenscore to determine the large language model has a hallucination or no hallucination. The sentence embedding Z can be obtained by averaging the token embeddings HT as shown here. Namely, Z is a sum of HT, or taking the last token embedding H capital T as shown here. For key generated sequences, the covariance matrix sigma of their embeddings is represented as here, where sigma captures the relationship between different sentences in the embedding space. Z is the embedding matrix of different sentences. JD is a center matrix. ID is an identity matrix, and 1D is a matrix of all ones. Eigenscore E is defined as a logarithm determinant of the covariance matrix sigma, as shown here, where DETX is the determinant of matrix X, and a small regularization term alpha IK is to make it full rank. The Eigenscore E is computed by using the eigenvalues lambda I, where lambda is eigenvalues of covariance matrix, which can be obtained through singular value decomposition. For more details, please check with these references. Thank you.